In this next example, we're going to try to find the solution of an initial value problem analytically. And in fact, I want to solve two initial value problems, the one on the left and then the one on the right. So we have the second order equation. In fact, this is second order linear equation because it looks like a sum of a function with its second derivative with coefficients that are independent of the function, of a known function. And suppose that we're given that this equation has this two-parameter family of solutions. First, I want to verify that indeed the circle function always solves ODE. And then once we demonstrated that indeed this is a one-parameter family of solution, two-parameter family of solutions, sorry, because we have two parameters, C1 and C2. Once we figure this out, then we want to determine the constants C1 and C2 from initial conditions. Okay, so if y is like this, then what we have is that y prime is, let's see, so y prime is going to be C1. Derivative of the exponential is itself, and we use a chain rule. Derivative of minus 2x is minus 2, plus C2 e to the 2x times 2. That's the first derivative. Then the second derivative is going to be, so repeat this again, C1 e to the minus 2x, derivative of e to the minus 2x is itself. And the chain rule brings down another minus 2, so minus 2 squared, plus C2 e to the 2x, another 2 comes down, times 2 squared. Now, 2 squared or minus 2 squared doesn't matter. Both are equal to 4, which I can pull out to get 4 C1 e to the minus 2x plus C2 e to the 2x. And now if I compute y double prime minus 4y, then y double prime I just figured out. And I need to subtract 4 times y, and y is this quantity here. And obviously, if I open the parentheses, right, then negative powers cancel out, positive powers cancel out, and this is 0. So therefore, y is a solution for an arbitrary choice of C1 and C2. Okay. All right, so now let's solve the initial value problems. Let's denote this as initial value problem number 1. And this would be initial value problem number 2. So to solve 1, what do I know? I know that, let me actually simplify this expression here because we'll need it. So I have 2 times, if I factor out 2, minus C1 e to the minus 2x plus C2 e to the 2x. All right, so what do we know? That in problem number 1, we want to have y of 0 equal to 1 on one hand. And on the other hand, y of 0 is this expression computed at 0. So this should be C1 e to the minus 2 times 0 plus C2 e to the 2 times 0. E to the 0 is 1, so this should be C1 plus C2. And then y prime of 0 in initial value problem number 1 must be 0, right, as we see here. And what is that? That's a derivative of y, which is the thing that I simplified here, evaluated at 0. So it should be twice minus C1 e to the minus 2 times 0 plus C2 e to the 2 times 0. Again, e to the 0 is 1, so this should be 2 times minus C1 plus C2. Okay, so then from the second equation, we have that C2 minus C1 is equal to 0, and then from the first equation, we have that C2 plus C1 is equal to 1. And then, for instance, if I add two equations, I'm going to get 2C2 is equal to 1 because C1 will go away. So therefore, C2 is equal to 1/2. And then from the first equation, C1 is equal to C2. And so therefore, C1 is also 1/2. And so then the solution to the initial value problem problem 1 is y of x equal to 1/2 e to the minus 2x plus 1/2 e to the 2x. Now let's look at the second initial value problem. Here we have y of 1 equal to 0, y prime of 1 equal to e squared. So we're solving problem number 2. So again, on one hand, y of 1 is equal 0. If y of 1 is equal to 0, then we have y of 1 on one hand is 0. On the other hand, it is whatever this expression is when x is equal to 1. So when x is equal to 1, 2x is 2. So we have C1 e to the minus 2 times 1 plus C2 e to the 2 times 1. So C1 e to the minus 2 plus C2 e squared. Right? And then the second condition is y prime of 1 is e squared. So y prime of 1 is e squared on one hand. On the other hand, it is the expression that I see down here when x is equal to 1. So it's 2 times minus C1 e to the minus 2 times 1 plus C2 e to the 2 times 1. Let me check. Yep. So that is to y's minus C1 e to the minus 2 plus C2 e squared. Okay, so then we end up with two equations. So therefore, number 1, C1 e to the minus 2 plus C2 e squared, that is equal to 0. That's the first equation. And the second equation, if I divide both sides of this by 2, I'm going to get that minus C1 e to the minus 2 plus C2 e to the e squared, sorry, that is equal to 1/2 e squared. So C1 and C2 will satisfy these two equations. So therefore, if I add the equations just like I did in the previous example, I'm going to get C1 will cancel out, and I'll have 2C2 e squared equal to 1/2 e squared. E squared goes away, and so therefore C2 is equal to 1/4. And then if C2 is equal to 1/4 from the first equation, I see that C1 e to the minus 2 plus C2 e squared is equal to 0. And so therefore, from here, it will follow that C1 is, so I move C2 e squared to the right-hand side, and I divide by e to the minus 2. Dividing by e to the minus 2 is the same thing as multiplying by e squared, so this would be minus C2 e to the 4th. And so therefore, C1, because I know that C2 is 1/4, so this is minus 1/4 e to the 4th. And so altogether then, what is y of x? So therefore, y of x, a solution of a second initial value problem, is C1, which is minus 1/4 e to the 4 times e to the minus 2x, right? Because we had C1 e to the minus 2x, plus C2, which is 1/4 times e to the 2x. Right, so that's a solution to the second initial value problem. All right, so next example. Let me move these ones. So next example, I want to verify that this function is going to be a one-parameter family of solutions, right? Because this is a first-order equation, I would expect that a solution of that will look like an one-parameter family of solutions. And then I want to solve two initial value problems that I listed here. Okay, so if I want to verify that something is a solution of a first-order equation, I need to compute the first derivative. So if I have y equal to y of x is x cubed plus c to the power minus 1. So then I compute the first derivative. That's going to be computed according to the chain rule. So y prime is minus x cubed plus c to the minus 2. Derivative of the outside function times the derivative of the inside function, so times 3x squared. And so then substituting into the equation, and what are we going to get? So equation says that I want to compute y prime plus 3x squared y. What is that? That's y prime that I just figured out. I'm going to move 3x squared to the beginning, so minus 3x squared x cubed plus c to the minus 2 plus 3x squared, sorry, y squared, x squared y squared And who is y squared? It's our function y listed here squared. So x cubed plus c to the minus 1 squared. All right, but then power minus 1 squared is power minus 2. So this is minus 3x squared x cubed plus c to minus 2 plus 3x squared x cubed plus c to minus 2. They cancel and you get 0. So that means that indeed our function is a solution which depends on an arbitrary constant. So that means that this is a one parameter family of solutions. So hence this is a one parameter family of solutions. All right, and so now let's try to use this to solve the initial value problem. I finish writing this. So once again, let's call them 1 and 2. Solving 1, I need to satisfy the initial condition. Initial condition in 1 is y of 0 is equal to 1. So on one hand, 1 is y of 0. On the other hand, it is whatever you get from our y of x, substituting 0 in it. So it's 0 cubed plus c to the power minus 1. And so c to the minus 1 is equal to 1, so therefore c is 1, and the solution of initial value problem 1 is y of x equal to x cubed plus 1 to the power minus 1. Okay, and lastly here, we're going to solve problem number 2. What we're going to get in this case, y of 1 is equal to 0. And that should be the same thing as this function evaluated at 1. So that is 1 cubed plus c to the power minus 1. So what have we got? We got that 0 is equal to 1 over 1 cubed is 1 over c plus 1. And that's a problem. We cannot solve for c. And because we cannot solve for c, right, because then if I multiply both sides by c plus 1, I get 0 equal to 1, which is obviously not going to work. So that means that I cannot get a solution from one parameter family here. Okay, so from this one parameter family. So what am I to do? Let's look again at this problem. And let's forget about the fact that we had this one parameter family. Let's just look at the following. What if I have a function which is identical equal to 0? If I have a function which is identical equal to 0, then its derivative must be 0, right? So then I can immediately see that if I take a function which is identical equal to 0, then y prime is 0. This term is 0, so the equation is satisfied. And of course, if a function is identical equal to 0, then at 1 it is equal to 0. So that means that 0 actually is going to be a solution. So let me add a comment here. So note that y identically equal to 0 is a solution of the problem 2, but it is not a part of my one parameter family. So it just means that with ODEs, just like actually with integration, things are not always very straightforward. With derivatives, if you recall, right, it's always easy to compute a derivative because you follow a certain set of rules and everything works out. With integration, it's not like that. You always have to figure out what integration technique you're going to use in order to figure out the integral. So integration in that sense is akin to art, that you have to know what you're doing in order to succeed. Sometimes actually you cannot even find the integral. With derivatives, it's not like that. Derivative you can always compute. So with ODEs, it's kind of similar that if you follow rules, you will be able to find a solution sometimes, but at other times you'll have to figure out, to analyze your equation to figure out what the solution is. So let me just finish writing this here. So, but it is not of the form y equal to x cubed plus c to the power minus 1. So in this case, I had to observe that 0 actually is a solution, but it is not a part of our one parameter family. All right, moving on. Let's do another example. Let me see. So let me move this further down. So another example is that I want to demonstrate that all of these three functions, y equal to 0, y equal to x cubed, and this piecewise defined function, they're all actually solutions of this initial value problem, which will indicate to me so far the solutions that I found in previous examples. Each initial value problem had one solution. There was this strange case in when we solved 2 here, but at the end of the day, we still found only one solution, y equal to 0. So in this problem, I want to demonstrate that actually your initial value problem can have more than one solution. And let's try it. So if I set y equal to 0, then clearly y prime is 0. And then y prime, just like I said, it is equal to 0, but also 3xy to the 1/3, that is also 0, right? So both of those are 0, and so then, actually let me write it in a slightly different way. So both of these are 0, and so therefore the equation is satisfied. So equation is satisfied, and the initial condition, of course, is satisfied because if y is equal to 0 everywhere, then it is equal to 0 at 0. Let me use actually this notation instead of y equal to 0. Y, instead of equality sign, I'm going to use equality sign with 3 lines. So when I use 3 lines, and I'm saying that y is identically equal to 0. So it's not that y equal to 0 at some point, but y is equal to 0 at all x. So this is what 3 lines are going to mean. Okay, so 0 is a solution. All right. So equation is satisfied along with the initial condition. Okay. Okay, so that is number 1. Number 2, let's say y is equal to x cubed. If y is equal to x cubed, then y prime is 3x squared. And if y prime is 3x squared, so then I'm going to substitute, that's what I'm going to get on the left-hand side of my equation. Let's see what about the right-hand side. 3x y to the 1/3. If y is equal to x cubed, this is 3x times x cubed to the 1/3. X cubed to the 1/3 is x again, so this should be 3x times x, which is 3x squared. And so therefore, in this case, what I got is y prime is the same thing as 3x to the x times y to the 1/3, because both are the same and equal to 3x squared. So that means that the equation is satisfied. And in addition to this, what about the initial condition? If I compute y of 0, then this is 0 cubed equal to 0. So initial condition is satisfied. So then we conclude that y equal to x cubed also solves the initial value problem. And finally, let's look at item number 3. Let's see the following. So what if I have y equal to minus x cubed? If I take y equal to minus x cubed, then certainly the derivative of that is going to be minus 3x squared. And 3x y to the 1/3 is going to be 3x times minus x cubed to the 1/3, which is minus 3x. I can pull out the minus sign outside of the cube root, so it's minus 3x times x cubed to the 1/3, and that is minus 3x squared. And so immediately what we see is that y equal to minus x cubed also solves my equation up here. All right, so the equation is satisfied. And of course, minus, so also minus 0 cubed is 0. So therefore, y equal to minus x cubed also satisfies the initial condition. So the initial condition is satisfied. So we conclude that y equal to minus x cubed also solves problem number 2. So already this initial, well, it's not, we don't have 2 here, so it also solves our initial value problem. So already this same initial value problem has 3 solutions, 0, x cubed, and minus x cubed. And now I'm just going to demonstrate quickly why the third function, the fourth function, is also a solution. So, and I'm going to demonstrate this graphically. That function is defined piecewise here, right? And I'm just going to draw its graph. So it is going to be equal to x cubed on the right-hand side of y-axis, and it is equal to minus x cubed on the left-hand side of y-axis. But I already know that on this side, what I got is a solution. On that side, what I got is a solution. Now, these two functions, x cubed and minus x cubed at 0, are both equal to 0. So this piecewise defined function will have will satisfy the initial condition y of 0 equal to 0. And furthermore, the slope of x cubed and minus x cubed at 0 is equal to 0. So the slope of this function, which is composed of, actually, I'm sorry because my graph is nonsense, right? Because minus x cubed will look like this, but it doesn't change the substance of what I'm saying. The slope at 0 of both pieces on the right and on the left is equal to 0. So that means that both the derivative and the function itself are defined at 0, and the derivative is equal to 0. And so that means that actually the composite function is also a solution of my ODE. So the conclusion is that the initial value problem, this IVP, has at least 4 solutions. Actually more, but we're not going to discuss it now. And then the final example, before I move on with this in the next lecture, the final example, I want to demonstrate that this initial value problem that I'm writing here actually has no solutions at all. And how can I demonstrate that? Let me see. Actually, let me do it in the next lecture. So I'm going to stop here, and then we'll continue in the next lecture.